right, so we're going to go ahead and dive into our first example of Poisson regression here. So here looking at the number of customers and town size. So we recorded data for a small chain of stores, and they're interested in the number of customers that they receive. So this is going to be our Y that we're working with in a day based upon the size of the town in thousands. So this size of the town in thousands is going to be our X variable. For every ith store, we're going to assume that the number of customers, yi, has a Poisson distribution with mean mu(i), which will be dependent upon the town size. We're going to model the expected number of customers using our Poisson regression model. So we're going to have that the log of mu(i) will be our alpha plus beta xi, or we could say that mu(i) will be e to the alpha plus beta xi. So we're going to go ahead and fit this model in R. So you'll see the code here, but I'm going to kind of run it in R, and then we'll kind of come back here and highlight things as needed. So the first thing I did was just load in my data set here into R, and I called it cust so that it'll work coming in here. You'll notice with the function, I'm still using the function called GLM. My formula is still y tilde x, and again, those names come from how they're named in the actual data set that we're working with. So I got to make sure that they match. So that's why it's pulling that data set. For the next part, for the family, this is where it's different than what we had for logistic regression. So before we had binomial, now we're using Poisson because we're working with a different kind of response variable. We're modeling count data instead of a binary response variable. The link function we're going to use is the log link function. And then everything else here in the controls is the exact same that we had with logistic regression. So as that's highlighted here in your notes for you, this is really the main difference. Of course, what Y actually is now different. It's no longer a success failure, so it's no longer just zeros and ones that we're working with. But inside the actual code, this is really the main thing that's changing, is we're using a different family of link functions, and then also, of course, specifying which link function that we're going to use. Then it's just giving you that information if it's converging as it's going. And then I'm just going to spit out what's inside that mod.fit by saying summary of mod.fit. So we have that same code in here. So we'll go ahead and just run those two lines. So again, there's our first part of the output. And then again, and inside that summary, the main thing I'm going to want here is this alpha hat and beta hat that it's given me. That's going to be our main focus right now. So again, that's our main difference in the actual function. Here is going to be my alpha hat and beta hat. So I'm going to use those numbers as we go then to the top of the next page to write out my prediction equation. So I can say then that mu hat is going to be e to my alpha hat, so this 4.247 number, plus our beta hat, which is actually positive, so this number we see there, times our x. So there is our prediction equation. So now we could use this prediction equation to find the predicted number of customers per day in a town with 10,000, 30,000, or 150,000 people. So if we're interested in 10,000 people, That means I'm actually going to plug in an x of 10, because remember it was measured in thousands of people already. So I would just plug in 10 for my x. And we would get 75.3. And it's actually okay for me to leave this as a decimal because we are predicting technically the mean number of customers in a day. So saying a mean of 75.3 customers in a day is okay. Now if instead I was interested in the 30,000 people, we would just plug in an x of 30 instead. So the exact same equation, but except for where I have the 10, we're just plugging in 30 instead. And this time we get 87.3 average customers per day when you have 30,000 people. And then if I was interested in 150,000 people, I would just plug in an x of 150 instead. And it would give me 211.7. So there are some different predicted values just using the equation. However, of course, we could use R to do this prediction for us. So we're going to be using that predict function inside of R. Things I need to, of course, have done this is I need to store my function that I used. So that's kind of, again, one of the reasons I put this in this thing called mod.fit is so I can actually use it for our prediction part. So I'm going to do the same 10, 30, and 150 that we have above. Again, when I'm actually going to want to use this, I'm going to put it in a data frame, and I've got to use the exact same name that the variable is called inside my actual mod.fit. So it was called town.1000s, and I'm going to put inside that the 10, the 30, and the 150 to match what we have up here above. Since I'm also going to go ahead and do a confidence interval with it, I'm also going to set my alpha to be able to use. And so I'm going to predict for this data. I'm technically doing it here the not as good way because I'm using that type equals response. So remember, when I do it that way, this is technically the not as good way. But again, just for demonstration, it's nice to see. Standard error equals true is going to allow me to help me construct that actual confidence interval. So then I'm actually just going to use that fitted value and the standard error, do the lower and the upper main difference, again that plus or minus, put it all in a data frame and spit it out. So the same process that we did with the logistic regression, it's just now we're working with a different type of model instead. So running that code here. Here's our output. So first, and let me do it out here where we can draw on it here as well. So the first thing that we see here, this mu dot hats, let me kind of like label and structure around it, are these first numbers that we see. And those are the ones that we got when we just plugged in our values into the equations themselves. So that's exactly what R is doing there as well. But now the confidence interval is using that standard error to help us construct that. And you'll notice that the width of the intervals is different because they can have different standard errors, especially based upon how much data they have around those values that you're trying to plug into your equation. Again, if I wanted to do it the better way, I would technically use the link function and then have to raise e to my interval. We won't worry about that here. It's just more for demonstration. Right, we're also going to go ahead and look at a plot of the data with the fitted equation on it. So for the first part, we're just going to worry about actually getting the plot of the data. Here, since I'm already working with two quantitative variables, I don't have to worry about summarizing them first. I can actually just get a regular scatter plot of my data, where my X is that town size, and my Y is just my number of customers. These are just my labels I'm putting on my X and Y axes. Main is again just the overall title that I want to put on my plot. And this panel.first is going to help me kind of put an actual grid so I can see that on my graph. So let's actually just run that part of the code here first so you can see what that looks like. Let me go ahead and clear the plot I already had here. So you can kind of see as just I run that part, what do we get? So first we're just going to get a plot of the actual data. So we can see the different town sizes. So we have a lot more data here between a town size of 0 and 50,000 than we do between 150 and 200,000. That kind of helps explain our widths of our intervals that we just looked at. So here's just the town size in thousands and then the number of customers. I let it use the axes and kind of come up with the limits by default. If you wanted to start this one at 0, you could force it to if you wanted. The next thing I want to do is actually put my fitted line on that. So what I'm doing here for my lin.pred, so let me go here where we can write out what we're doing. So with this lin.pred, what we've just done is this is just doing the alpha hat plus beta hat times x. So the alpha hat's just that mod.fit, the first coefficient. Our beta hat's the second coefficient. And then we're going to multiply that by our town size. So this technically should say town.thousands. And I'm going to try to fix that in your handout so you have the right one there. So we're going to multiply it by that town size, our x, to get that value. Then to actually find our mu hat, we're going to do what we had to do up here. We're going to take e raised to that value that we had. So that's what this is. This part is doing. The e is to the alpha hat plus beta hat times x. And now I'm going to fit that line. So this is my model. So we're going to fit that line for those different x values. And the y is going to be this predicted value. And then I'm just coloring it blue here. So when I run this lines function, it's going to put a line over whatever plot you currently have up. So make sure it is the right one. And so there is our predicted values to go along with it. And remember, this is our predicted mean value versus, of course, the dots are the actual values that we had for those different stores that we were looking at on those days. So this will give you guys an idea of if the model seems to be fitting very well. Here, since we actually have all the individual data points, I can see that I have a lot more data down here than I do up here, so it's a little bit easier to see. We really want the fit to be really good down here and maybe expect it not to be as great for these larger values because there's not as many data points there to be working with. The last little part here before we stop this video, move on to a next one, is again when you're looking at this code, when you see those plus signs, that technically means that it was just the ran code that's not part of the actual code when we look in here. So there's no plus signs. It's just because it went on to the next line of the code there. All right, we'll do another example in the next video.